Hi. So, I kind of want to confess something. For a lot of my life now, I have really had a problem with calculus. I mean, I think many people relate to that since calculus obviously isn't taught particularly well, but I've always, even when watching maybe some of the best content for learning calculus, been at least a little bit uncomfortable with its ideas. Namely, there's always this one thing that's hand-waved all the time in traditional calc that I've always found weird. Whenever dealing with calc, I think the thing that you do pretty much all the time is saying, okay, let's say you have something that you want to calculate that isn't very easy to calculate. For example, for this x squared graph, we might want to find something like the line tangent to a point. Or for some other examples, we might want to find the area of some curve or the sum of some infinite series or something like that. For example, for finding the slope of any point on this graph, we might give some approximation with a right triangle here, and then do the algebra for the equation of the slope. Then, if we make this approximation better and better, reducing some dx term, it gives us a better and better answer since the slope seems to be approaching the slope of this particular point. Which, okay, sure, yeah, the approximation itself does get better. But then, if we magically take this dx to 0, somehow it gives us a weird kind of exact answer to this question in full unapproximated position, even if that doesn't make sense because, say, we're dividing by 0 here. And when you ask about it, they kind of say, oh, don't worry about it, because we're only approaching the value. It's not actually a division by 0 or something like that. Namely, it's mostly just, oh, trust me, this works. Generally, in calculus, it's this idea of taking something to infinity, or doing something infinitely many times, or adding up infinitely many things, or having some value get infinitely close to another value, that I've always found kind of unfathomable. It's insane to me that all of that would actually rigorously work. Now, this idea is often hand-waved for a very good reason. It takes a really long time to fully develop, and even the founders of calculus took a really long time to fully figure it all out. But I still really wanted to know why this worked in such a pretty way, and I would often hear that an area of math called analysis was exactly where people tackled these weird things we got out of playing with infinity. So I tried to learn analysis, and I wanted to give you a taste of how a tiny sliver of it works here. However, before we even try to get at the inner machinations of derivatives and integrals and techniques and results, and even some of the eldritch horrors of analysis, I want to start with the groundwork and really dig into one of the first foundational ideas of calculus, convergence. Specifically today, I want to talk about convergence of sequences. Let's say you're watching this little hamster who's, to put it formally, having some mild zoomies. You notice that this hamster is particularly moving along this straight line. The hamster moves, say, 1 meter in a small portion of time, then stops for a bit, then they move half a meter again, then stops for a bit, then a fourth, then an eighth, then a 16th, etc., etc., etc. Now, I ask you, if we gave it enough time, what do you think would happen? Would it fly off the Earth? I mean, it certainly doesn't seem that way. It seems to not get past a particular point. Do we think that they might be trying to approach a particular point here? Maybe you've even been told that it's approaching this point, which is exactly a distance of 2. But the mathematical machinery behind why we can actually say that is what we're going to develop in this video. Now, we're most used to thinking of points getting closer to a particular point in a line or plane of real numbers. But there's also a similar idea of certain sequences of polynomials getting arbitrarily closer to any function you want, or certain sequences of sine and cosine functions getting arbitrarily closer to any periodic function you want. All of these touch on one of the foundations of how calculus works, convergence, where we try to make precise this notion of a sequence of things getting closer and closer to a particular other thing. Now, I don't have the time or knowledge to go through all the different types of convergence, but here I'll talk about this particular convergence of a sequence of things. And the central idea we'll be using to analyze this, along with, well, all of analysis, is the concept of a metric space. Now, our problem of a particular sequence approaching a particular point only really makes sense when we can kind of say that the point's distance to another point is decreasing in some way. So To do this in analysis, we use the concept of what we call a metric space. A metric space, in simple terms, is a space with a metric, where a space really is just a fancy word for some set of things, be it numbers or hamsters or points in the 2D plane, and a metric is some distance function, where we can take any two things from the set and we can calculate a distance between them for a particular notion of distance. For example, a sense of distance you might be familiar with is, say, the distance between points on the real number line, where we calculate the distance with this formula with the absolute value, or the distance on, say, a piece of paper, where the distance between any 2 points is just the distance formula, namely the Pythagorean theorem thing for any 2 points x1, y1, and x2, y2. We call this little glorified Pythagorean theorem calculation our distance function for this notion of distance, where the function takes 2 points in some set of numbers and gives you back some number, particularly a non-negative real number. For a more unexpected example, say if you have a graph of some social circle where everyone who's like socially close to each other is connected, you can actually calculate how socially far apart you are from someone else by counting the lines of the shortest path between you two. For example, here in this graph, the distance between Charlotte and Felix would be 1, which is pretty close, and the distance from Henri to Florence would be, well, the shortest path you can take here, which is 3, and that's pretty far away. Facebook uses graphs like these to figure out how to sell you stuff. Now, fortunately for us, this distance function d isn't just any old function. This function has 4 particular properties that it has to satisfy that really tries to capture our intuitive notion of distance and allows us to work with this function better. The 4 properties are as follows. First of all, distance has to be greater than or equal to 0. This, corresponds to our idea that distance can't really be negative. Note that for some distance, say the distance between numbers on a line, it can be unclear whether going from, say, -1 to -5 is going 4 units or -4 units. Here we take the absolute value to fix that. Number 2, if the distance between 2 points P and Q is equal to 0, that means that P and Q are actually considered to be the same point. This can actually get a little bit confusing because in the consideration of, say, the set of points we're using, these points may be completely different. But if the distance between them is 0 within some metric, we consider them to be equivalent or really equal. Really kind of like different variable names for the same exact thing. Number 3, the distance from P to Q is the same as the distance from Q to P. So whichever way you go doesn't really matter. And this final one, the triangle inequality, is a really important one. The distance from P to Q should always be less than or equal to the sum of the distance from P to any other point M, and the distance from that M to Q. The idea is that going from point P straight to another point Q should never be greater than if you took a detour. Now, you can check that the examples I just gave satisfy these properties, and note that as I've said, these distance functions are what a metric is, but usually we might just call it a norm. Other really fun examples of metric spaces are, for one, the space of all continuous functions on a certain interval that don't go off to infinity, equipped with something called the supremum norm, where the distance between any 2 functions is the biggest distance between the y values of the functions when you input the same x value to them. This is really useful when you start talking about convergence of functions. If you're a computer scientist, you might be curious about the distance between 2 binary strings so you can understand if it's likely that errors caused the bits to flip from one to the other. The shortest edit distance between them is something we call the Hamming metric. For the real numbers and the real plane, then the real 3D grid, and even the real 4D grid, etc., we have what's called the Euclidean norm, where it's just the Pythagorean theorem distance formula applied over a bunch of axes. And the absolute value definition is really the same as the principal root thing here. I'd also like to highlight that one thing can have multiple choices of metric. For example, for the real plane, there's another metric we can use called the Manhattan metric, where we add the x difference and the y difference between the 2 points. This can be relevant, say, in the super grid-like streets of Manhattan, where you realistically can't go from one place to another in a straight line, and have to go along the vertical and horizontal streets. Quick note, you might know that we denote the real line as R, but other than that, we also call the real plane R2 and the real 3D grid R3, etc., etc. When we illustrate metric spaces, we often draw points on a plane like this, and then have them be closer or farther apart, depending on the distance between them or according to our particular norm. But I hope you're not fooled by the fact that this looks like it's on a plane. These points really can be anything from nodes on a graph to continuous functions from R to R, and the distance between them is certainly not always the Euclidean norm. So I want to define a super important concept in the study of metric spaces. To better understand a particular point on a metric space, we use this concept of an open ball around that point. It's really a formal way to talk about all the points close to that point. Let's say we're in some metric space. To define it formally, an open ball of radius r centered at a point P is just all of the points that have a distance less than r from P in that metric. For example, in our 2D plane, say the open ball around a point P literally looks like a ball, since really we're asking which points satisfy this particular equation, which is just an equation for the inside of a circle centered at the point P. Also, I want to note that these points on the boundary, namely the points where the distance between that point and P is equal to r, are not included in the ball. With a bigger radius, the ball gets bigger. With a smaller one, it gets smaller. The open ball of R3 is really just a sphere around that point, kind of similar to R2. And for a 2D space, it's really just the open interval P minus R to P plus R. But for other examples, the open ball in the Manhattan metric looks like a diamond, and for the continuous function metric space, it's just this space around the function. By convention, we mostly just draw a ball to indicate all of these, but I hope you know that a ball can mean any of these separate things. Also, note, it looks like here that there's a finite amount of points in every metric space, but for most metric space, there will be an infinite amount of points, like with the real plane, for example. Now, there is a lot more we can talk about regarding metric spaces that come into play later in analysis. We can talk about interior points and limit points and open sets and closed sets and compactness, but I unfortunately don't have the time to get into all of that in this video, so we'll just have to leave that aside for now. With these ideas at play, we can actually do a lot of things. Namely, if we were able to make a definition or prove some result in general metric spaces, which we are going to do, we've not just proven that for R or R2, we've proven that for any set of numbers equipped with some function with these properties. That's the real power of metric spaces. Now, finally, we have enough to talk about general convergence. When we try to reason about with it, you'll see that it gets a lot more tricky than you would think at first. So first of all, to really just define a sequence is really just, well, a sequence of values, p1, p2, p3, p4, p5, dot, 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 that go on to infinity. And so they're countably infinite and can be listed here. Now, we think that a sequence that converges, or well, a convergent sequence, likely looks something like this. We can see that all the points Pn are closing in on something, maybe some point P. What if this point Q is kind of close to P, but is still pretty far away? It seems like there's a point here that it converges more to, but what would really be the difference between these 2 points when it comes to convergence? Well, it seems like it doesn't really get close if all of these points have at least some minimum distance from Q. To think of this in maybe a more comprehensible way, maybe if we can find some distance r of Q, where no point is less than that distance away from it, it likely wouldn't converge, i.e. if we can find some open ball of radius r where there aren't any points of the sequence. In fact, here we have an infinite amount of open balls where that's the case, with the biggest one being when r is equal to the minimum of the distance between P, N, and Q. Given that we can kind of conjecture some kind of definition, maybe we can say if we want some sequence to really converge, it has to get as close to some point as we want it to. So maybe we can say given an open ball of some distance epsilon around P, we can always find at least one Pn in this ball. That is to say, give me any distance, however small, I can always find a Pn such that they're even closer than that distance. This is always closing in. Well, you run into a problem here with this definition, and that's that all the points of the sequence are convergent points. Look at the set here that flies off after a P19, for example. It clearly doesn't look like a convergence. For any point, since all open balls of the point contain itself, this likely wouldn't work. Okay, well, what if we said we didn't include points of distance 0 in this open ball? I mean, that sounds reasonable. Well, if you do that, you run into another problem. What about some sequence like this, where Pn is literally just one point over and over and over? Does this converge? Well, it's certainly a weird kind of convergence, but it's definitely very, very, very close to a point, that point being itself. So, I mean, we would hope that our definition of convergence does fit this. But in this case, since we consider all points of distance 0 between each other not to be included, we can't say it does under our definition. So I don't think we can really use the unless d of Pn and P is equal to 0 part of our definition. Here, the issue was that while it did go 0 distance to a point, it never really did that again. Maybe we have to make it such that you have to have all the points consistently getting closer, i.e. the distance is always smaller than or equal to the previous distance. I mean, maybe we can try that definition where for any open ball there is some point Pn in it, and then that, say, d1 is greater than or equal to d2 is greater than or equal to d3, ... Except we wouldn't be including a sequence like this, which also looks like it converges just because it strays away for a bit. So I guess that definition was a bit too strict. Okay, well, maybe it kind of just has to decrease sometimes, but consistently. So like we can find a Pn in any ball, and then for any point Pn, there will always be a point later in the sequence that has a distance less than or equal to the Pn distance to our point of convergence. So just these two particular conditions. This definitely feels like it might work, because like given some PA, it has some PB, and PB has some PC, and so on and so forth. But what about a sequence like this, where it's kind of alternating between 2 points? Well, I mean, we might be able to say that it has kind of a cyclical nature, but I mean, we can't say it's true that it converges to a particular point. It almost can't make up its mind about where it wants to converge. Except clearly for any point in an open ball, all the even points after it satisfy our condition. So this definition ended up being too loose. We can actually say that certain subsequences of this sequence converge to a point, but I wouldn't think that for the main sequence. I think a takeaway here maybe is that making this definition is hard. But you know, with this example, sure, we might have a few stray points or many stray points here and there, but after some Pn, all of the points beyond that Pn are always in this open ball at this point. That's true of any of these open balls, where there's always some point Pn after which all the points are in an open ball. In some sense, for a point to converge, there must be finitely many stray points before it truly does start converging. This is where we get to our actual canonical definition of convergence. A sequence Pn converges to a point P if for all reals epsilon greater than 0, the distance between P and Pn for all n greater than or equal to some big N is less than that epsilon. Now, that's a mouthful, but like, let's say we have a distance of any epsilon we want around this point P. If Pn really converges to P, there should be some point beyond which all points are in this little epsilon ball of P. And well, this should be true no matter what ball we're around. That is to say, all points Pn should be close to P, including and after the point Pn. This avoids the issue of our cyclical cycle really easily, and it's pretty much the best definition we could think of without being too restrictive. I wanted to introduce the definition this way because I think that when you see the definition at first, it seems really weird that that would actually be the definition we use, but in the end, if you really think about it, it makes a lot of sense that it is this way. And this is where we actually get to test this on our first concrete example. We can think about the hamster example in terms of sequences, where the sequence kind of looks like this. First of all, for any of the expressions in these sequences, we need a form that we can manipulate a bit better. Let's try to take one of these expressions, say for the one on P5. Something interesting to notice is that if we added 1/16 to this, the sequence folds in on itself in the following way. The 16th and the 16th fold in to make an 8th, then that 8th can fold in on this 8th to make a 4th, and then the 2 fourths here make a half, then the 2 halves here make a 1, and then the 2 1s finally make a 2. Therefore, really, if adding 1/16 to this expression gives us 2, then the original expression is just 2 minus 1/16, i.e. 2 minus 1 over 2 to the fourth, for P5. Similarly, it's 2 minus 1 over 2 to the fifth for P6. And generally 1 over 2 to the n minus 1 for Pn. Okay, and now we can get a little more started on the proof. So remember, what the question is really asking is whether for every epsilon you can find me a big N such that this condition works. The way we're going to do this is, well, first of all, let's fix an epsilon here. We have to find the starting P big N such that the distance from P big N to P is less than epsilon. Well, here for R with the Euclidean norm, we have this particular absolute value distance function. Our P of big N can be represented as this, and our P can be 2. Notice these 2's will first of all cancel. Now we can get rid of the absolute value here, since 1 over 2 to the big N minus 1 is always positive. And now we can work out some algebra, like here we can reverse the reciprocals, then take the log, and then we find that for this expression to be true, big N has to always be greater than this. Now, it's usually nice to have an explicit expression for big N where it equals something. It's even nicer if it's an integer, so just to make sure that big N is greater than this, we just take the ceiling and add 1. You'll notice that big N can be negative sometimes, so we can indicate that we take the maximum of 1 and this if we want. Now that we've found our big N, we can actually go to the proof. Here's what's magical about this big N. If n is greater than or equal to big N, and big N is greater than log 2 of 1 over epsilon plus 1, then n is also strictly greater than that. So after some algebra that is pretty much the same, we see that 1 over 2 to the n minus 1 is less than epsilon. Well, okay, given that, let's consider all of the distances d of Pn to P, and this is really just the same as this. But wait, when n is greater than or equal to n, 1 over 2 to the n minus 1 is less than epsilon. So this entire thing is less than epsilon for any epsilon, however small we choose. So for all values of n equal to and after big N, all of this works, i.e. for any open epsilon ball around 2, all of these points will always be less than epsilon. And so we're done. The hamster sequence really does converge according to our most sensible definition of convergence. Really, the way convergence proofs tend to go is we fix some epsilon, find an n that works, and prove that that n works. You can actually see that any other value for the point of convergence would not work. For example, 2.01, because then we can find an epsilon, say 0.005, where this distance can never be smaller than that. You can actually also see that other sequences don't converge, like for example, if say the hamster was moving a distance of 1 every time, then no positive real would satisfy this condition. Now, unfortunately, I only have the time to show you this for R, but theoretically, we can actually do this in a lot of other metric spaces. We can prove convergence for things in the complex numbers, or in the continuous function space, or even for Hilbert curves. And I'm really sad that unfortunately I won't be able to get into all of that. I hope I've been able to give you a taste of convergence and what real analysis is like. There are a lot of other directions you can go in analysis. For example, you can talk about this property called compactness and how it relates to subsequences of sequences. You can talk about continuity, you can talk about derivatives and integrals. But I hope you know that for all of these concepts that seem super weird and super hand-waved, there's actually a completely justified explanation for why we do the things that we do. And I think that's really great. I think that's amazing that that is the case. But yeah, that's all I have for you, and I hope you have a good day.